I apologize for not having all of your unit tests graded.
Did you do mine?
I don't believe so. I actually got to Russell, and then I ran out of time. I couldn't even grade yours. And I haven't seen anything.
Okay, good.
And I think that's in the J's. So I'm like, well, actually, I think I'm almost halfway through grading them. You would have been halfway or something. And I did not get there. However, we can talk about part A. How did you guys feel part A was? What you expected? Good. Were there any on there that you were upset to see or excited to see? Confused about seeing?
I was confused about one, but can I remember how to say it without pulling it up? No. That's exactly what I'm doing.
Wow, guys, this is a really high average. 92% average.
The low, that was me. Just hold them down.
Funny.
That's not even a low. An 80%?
You don't even want to know how.
By the way, that's not just one person. That's like 3 or 4 people, according to this. Pretty remarkable. Even my OCHEM 1, who had their unit test this weekend, their average on part A was an 87%.
Wow.
High B. But they're doing reactions for the first time, you know? So they had to classify addition, elimination, substitution, predict whether the carbocation shown will shift, which carbocations will shift, what reagent is needed for the product shown, what product is formed, what missing stereoisomer is formed, what missing structural isomer is formed, all sorts of fun stuff.
You haven't done addition or...
They just did their
Yes,
addition
and then
reactions.
you have
Yep, they're going to do substitution elimination this unit. For part B, I do not yet have all of the statistics, but I can show you how the first half of the class did. Well, I guess that's kind of rude, isn't it, to show how the first half did. Okay, so this is saying 13 students have a 0. That's to say that I did not grade 13. And then we've kind of got this distribution, and you can see the higher amount is on doing well. And then there's kind of this distribution of having some mistakes somewhere between mechanisms and the multi-step synthesis. In terms of the multi-step synthesis, this time I didn't just give you starting material and product, but I told you try to have 3 steps. Yay or nay on that? Helpful? To kind of guide you and say make sure that you can do it in this many steps, rather than having you guess how many steps to have to do it in. Because when it comes to 3 steps, I was worried that you would spend too long realizing that it needs to be 3 steps and not just trying to do a 2-step mechanism, a 2-step synthesis. Okay. So I'm going to try and finish the grading of that unit test tomorrow, as well as all of the written work by the end of the week. Now we're on to our final unit. And for those of you that like to download things, I believe I've already uploaded the documents you need. I've uploaded the learning objectives for Unit 5, as well as the worksheet for today's class. Yes, Christina?
I actually did have a question about one of the questions from the unit test.
Dime, tell me.
It was one of the number 3s.
Yeah? One of them.
It was the one that asked which of the following is formed by the synthesis, and it was like a freedom cross acylation, like a greenery, and then plus and mag. If I put this as the answer, which was
Well, that seems like a mistake then. let me check that on my side. Haha, you can't see it. That what you showed seems like the most reasonable option, doesn't it? Can't possibly be anything else.
That's what I thought.
Because it's an aldehyde starting material, formal chloride,
Yeah.
an aldehyde
Yeah.
/ acid chloride,
Yeah.
formal chloride. One second, please. Unfortunately, these are kind of all over the place, so it's hard for me to find exactly. I am going to need to look through my quiz banks a little bit more to find this. Could you do me a favor and email me with that? There was also another one that I had a typo on. So I'll be going through. It was like, which of the following cannot synthesize this product? And one of them had the wrong carbon chain, but it was supposed to be an option that did form the product. So I will go back and give points. So technically there were 2 things that did not form the product shown.
Was it this one?
I will go through, I will go through and fix points for those. Also, there was a problem. I forgot I did this. There was a problem that had multiple correct answers. And I have to go through and assign partial credit if you got either one of those correct answers there. I created these quiz banks last fall. I don't remember doing this in the spring or during the summer. So, oops. I feel bad for... nobody pointed it out, though, which makes me think they felt pretty confident about what they had being wrong. So, anyways, I want to point out something about the learning objectives documents. Can you guys tell me, do you use these at all?
Yes.
Can you tell me how you use them?
To like make my own like study guides and like the cheat sheet for the midterm.
You use it to make the cheat sheet?
Yeah.
Meaning you check what reactions you want to have on there and what reactions you don't bother putting on?
Yeah, and just making sure I have all of them covered.
Mechanisms?
Yeah.
Make sure you aren't putting mechanisms for things you won't be tested on and do have mechanisms for things you will be tested on. How else do you guys use them?
Pretty much that. Knowing which reactions I need to know well.
Knowing the reactions to know. You'll use control find. Yeah. Good. Yeah. So that you get more exposure to it. So, for instance, reductive ozonolysis of alkenes. Copy and paste that into YouTube and then find a video that talks about it and gives more examples. Good. I wanted to point out our Unit 4 Learning Objectives document. 1, 2, 3, 4, 5 full pages. And to be fair, there's a lot of reactions that are on that document that are repeated. Under aldehydes, we said you can oxidize an aldehyde to create a carboxylic acid. And then under carboxylic acids, we said you can form a carboxylic acid by oxidation of aldehydes. So there's a lot of repeats, especially in the derivatives, where the derivatives can all go multiple directions. So you see these reactions show up more than one time. But 5 pages for 1 unit. That's a lot, right? All right, here's our learning objectives for Unit 5. Boop. Oh, just one little guy made it to the other side. That's basically one document, 1 page, I mean. Congratulations. We're in the home stretch, and this should feel a little bit easier. Cooper?
Yeah, I would write that too.
Yeah.
The objectives are all peer review.
I'll fix it. I copy and paste the document. I just make a duplicate of the document, and you're right. I did forget to fix that part. Thank you for pointing that out. You don't get a sheet anymore. So today we're going to start off Unit 5 by talking about alpha carbons and alpha carbonyls. This is one of our first learning objectives. It says this is the learning objective for Unit 6, but if we're being realistic, Unit 6. It says identifying alpha positions is a learning objective for Section 22, but if we're honest, it's going to apply to Section 23 as well. That's why these are a unit. They go together. What happened here? So if we look at a generic carbonyl, you know what? Actually, let's take a look at some types of carbonyls: aldehyde, ketone, and ester. And I am specifically drawing them all with this carbon here on the side, and then some R group. The anatomy of the carbonyl, if you will, involves the carbonyl carbon, the alpha carbon, and a beta carbon. If you remember in OChem 1, we referred to specific carbons as alpha carbons. Do you guys remember what might lead you to call a carbon the alpha carbon? Not in OChem 1. That's true here. But I want to make sure that you remember what we called alpha carbons before so that you can compare it to what we're calling them now.
Was it distance from a chiral center?
It was not distance to a chiral center. No. Usually actually not adjacent to the functional group. The functional group was considered, the carbon with the functional group was considered the alpha carbon. Alpha cleavage in mass spectrometry was where you cut the carbon-carbon bond adjacent to the functional group, which is to say, cut off the carbon, the alpha carbon, that has the functional group. So when we did elimination reactions, we said your alkyl halide is the alpha carbon, and then you have a beta hydrogen, and you run alpha-beta elimination, beta hydrogen elimination. Pretty much that was the only time we used it. Okay, so you would likely think the carbonyl carbon is the alpha carbon here, because that's the carbon with the functional group. The carbon of the carbonyl is often the functional group, but we're not going to say that. We'll say that the carbon of the carbonyl is the carbonyl carbon. We don't have a better name for it than that. I don't, anyways. And I speak on behalf of all of the scientific community, of course. It's the carbon adjacent to this that we call the alpha carbon. And this is what you were saying, Maddie. Aldehydes have how many alpha carbons? 1. Maximum. Formaldehyde doesn't have any alpha carbons. Any of your form groups. Formaldehyde, formic acid, formal chloride, formic anhydride, formate. All of those one carbon aldehyde groups have no alpha carbons. They're not attached to any other carbons. How about this ketone? How many alpha carbons on the ketone?
2.
2, 1 on each side. It's not a ketone unless it has 2 alpha carbons. How about our ester? By the way, these are the key functional groups that we'll be dealing with in this last unit. Aldehydes, ketones, and esters. How many? Just 1. The carbon attached to the ester linkage is not adjacent to the carbonyl. It's adjacent to an oxygen. So esters, 1 at most. I suppose I can show you these exceptions if we have formaldehyde or if we have formate. These would be examples of aldehydes and esters that have 0 alpha carbons. Great. What comes after alpha? Where would the beta carbon be here? It'll be this R group. This guy's beta, these 2 are beta, and this is beta. True or false? Every aldehyde with an alpha carbon must have a beta carbon. False. It might end right there. There might not be a beta. True or false? Every ketone has 2 alpha carbons. That's what makes it a ketone. It's got carbon on either side. True or false? Every ketone has 2 beta carbons. False. True or false? Every ketone must have at least 1 beta carbon. Also false. Acetone is a great example of a ketone that has 2 alpha carbons, as it must, to be a ketone, but no beta carbons, because those alpha carbons aren't bonded to anything. Okay, so we can see the dependence of the carbonyl on alpha and the dependence on alpha for beta. Beta is never a guarantee. Alpha even is not always a guarantee unless you're dealing with a ketone. I want to have you guys explore this a little bit more. It's not so much the alpha carbons that are important in the chemistry we're going to be doing. It's the alpha hydrogens. So let's take a few examples just to explore this phenomenon. This is called acetophenone. It's kind of like acetone, except that it's got benzene on one side. Acetophenone. How many alpha hydrogens are attached on acetophenone?
3 or 4.
How can it be 2 numbers?
No, it's not. It's just 3.
Just 3? Where was the 4 that you were thinking of?
I was thinking that it was either, so that's a ring, but I was thinking, how do you know if it's an alkene or an alkane? But it's an
It's not an alkene. It's an aromatic ring. But because it's part of the aromatic ring, it doesn't have any other hydrogens bonded to it. So this alpha carbon has no alpha hydrogens. We can say 0 alpha hydrogens. And here we have a position with 3 alpha hydrogens. So this carbonyl has 3 alpha hydrogens. And then I've got acetaldehyde. How many alpha hydrogens on acetaldehyde? Question mark? Does this hydrogen count?
No.
Why not? It's the carbonyl carbon's hydrogen. It's not an alpha carbon's hydrogen. So acetaldehyde also has 3 alpha hydrogens. So take this worksheet that you have in front of you and identify how many alpha hydrogens each of the carbonyls has. And if you can, distinguish between the two sides. If there's a ketone that has alpha carbons, alpha hydrogens on both sides, then list out how many alpha hydrogens on both sides of the carbonyl. Okay? Spend about 5 minutes doing that. The first 2.5 minutes, work on your own. The last 2.5 minutes, collaborate with the people next to you.
So this is just called the carbonyl carbon.
Carbonyl carbon.
Why are we using the carbonyl as the reference group?
I mean, do you want to say, like, why don't we give it a better name?
No, why don't we use this as a separate group?
There's a lot of chemistry that is relevant to how the carbonyl behaves with the adjacent carbon.
Are alpha and beta carbons and hydrogens only used for carbonyl molecules? So, amides, or ketones, or ethers? No, esters.
Can you ask the question again?
Are only carbonyl functional groups used for alpha and beta?
No.
You can use it for anything.
Anything that describes 2 adjacent carbons.
So this,
Alpha must be next to beta. That's why it's called alphabet, not alpha gamma bet.
why is it important to label a molecule by alpha and beta?
It's not. It's just convention. We could call it
What was
1
the
and
point
2
of the convention?
to say that they are adjacent to each other and the topic of focus.
Compared to the most active group, is there a group ranking that we'll have?
So we already explored carbonyl reactivity.
Okay.
We looked at the carbonyl reactivity for aldehydes, ketones, carboxylic acids, the derivatives, and nitriles. That was our unit 4. Now we're looking at the chemistry adjacent to the carbonyl, which is impacted by the nature of the carbonyl. We're going to find that there's resonance that the carbonyl can offer, and there's different reactions that can occur. We're using alpha and beta as a way to just localize the region that we're studying. The regiochemistry is just defined by these words. We could have used different words. I didn't have the choice. That's just convention.
So if you're describing the reaction in a paper, would you say I'm using alpha and beta relative to the distance from the carbonyl carbon in the paper?
Depends on what science you're doing. Yeah.
Chemistry.
We're going to learn a reaction that is said to produce an alpha-beta unsaturated carbonyl. So that already describes in and of itself carbonyl alpha-beta unsaturated.
What, like an alkyne?
Alkene. Yep, I'm going to put that on the board in a minute after you're done with this. If you haven't already, work with each other and communicate about what you found out about alpha hydrogens. Do you agree? Do you disagree? Are you confused by any of them?
Because the alpha carbon is only adjacent.
Is an alpha and a beta?
That's not carbon.
Yeah. Because there's like the ones that are next to each other.
Oh, yeah.
I didn't think on the other side of that.
Oh, look. Yeah, because that's what he asked us to do.
It does. It does. What you're going to say here is, because we're not worried about the beta carbons. We're looking at just the alpha carbons. Correct. Correct. So if a carbon is also a beta for some carbonyl, but it's the alpha of another. We'll count it as alpha hydrogens. Any structures that stand out to you as more challenging than the rest? No.
No tricks.
No tricks? Okay. Isn't that such a relief? All right. I guess it wasn't on this structure, was it? You were just thinking of that. There are some new functional groups that I want you guys to be aware of. And these functional groups are going to become a little bit more relevant in 23. But they can definitely be seen as relevant here in 22 as well. They're not even necessarily functional groups, just groupings of atoms that I want you to pay attention to because they'll become relevant. The first one that we can look at is this alpha halo carbonyl. It's as simple as saying at the alpha position, the carbonyl has a halogen.
Should we write this in?
This is a good thing to copy down. Pay attention to some new functional groups we'll be learning. Yep. I know this looks like I'm saying it's just for carbonyls, just for ketones, but it's really adjacent to any carbonyl. We'll call it an alpha halo carbonyl. If our alpha and beta positions have a double bond, we refer to this as an alpha beta unsaturated carbonyl. The term unsaturated there is describing what? The alkene. There's another name for this, which is a conjugated carbonyl. What is the term conjugated indicating there? Correct. Sharing of pi electrons. Or an uninterrupted series of p orbitals. P, 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 P. Resonance exists in this four-body system. It may look like there are two pi bonds, but there's actually one pi bond that exists across all four atoms, and another pi bond that exists in two phases with one node separating. And that looks a little bit more characteristic of what you see here. I think I'm getting ahead of myself by not explaining this. When you have 4 p atomic orbitals, then you get 4 pi molecular orbitals, the lowest energy of which is always in phase. That is to say, there's 2 pi electrons in this system that exist across all 4 atoms. Lewis structures are lying to you. One level up, and we introduce a node. So we get these 2 sets of 2 orbitals that are in phase, separated by a node. That resembles the 2 pi bonds that you see a little bit more closely. And then the next highest orbital has 2 nodes, which separates the atoms into these 1, 2, 1 groups. I ran out of space for the last one. It's the highest energy. They're just all 4 separated. And to be honest, it's not going to be something that you need to know, the all 4 separated. But I do want to talk a little bit more about these bottom 3 orbitals. How many of these have electrons in them? I told you the lowest energy does. Are there any other orbitals that have electrons? out of these orbitals, should there be any more that have electrons? How many electrons in my conjugated system? How many pi electrons in my conjugated system? 4 pi electrons. How many have I shown? 2. So there should be 2 more electrons in this conjugated system. That's going to go into the next lowest energy orbital. This is the HOMO, and this is the LUMO. Those are what we call frontier orbitals. They decide how reactivity is going to happen. With this conjugated carbonyl system, the alpha-beta unsaturated carbonyl, it typically gets attacked, which means electrons go into the LUMO. And what you'll notice about the shape of the LUMO is that it predicts a pi bond between the carbonyl carbon and the alpha carbon. That's going to be a characteristic structure that we see, where the carbonyl carbon and the alpha carbon become an alkene. That would lead to an alcohol or an alkoxide, a single bond there, and then some other hybridization here. We'll get back to that. So I want you to pay attention to this structure because it actually explains some of our reactivity. A couple of other functional groups. This is referred to as a beta keto carbonyl. It's a bit misleading. It doesn't actually need to be a ketone group. So we could call it a beta acyl carbonyl. Acyl describes what? Acyl does not describe carbon-carbon. What was acylation back in section 16? We took a ring and we acylated it. We added a carbonyl. When we do mechanisms and I tell you to show acyl addition, what do you attack? What do you add to? A carbonyl. So acyl just describes carbonyl. This would sound sillier if we called it an alpha carbonyl carbonyl, or sorry, a beta carbonyl carbonyl, but we could. So we could call it beta acyl carbonyl. It's more commonly referred to as a beta keto carbonyl, and one of the most common beta keto carbonyls is the beta keto ester. Do you guys see a beta keto ester on your worksheet? Good. This specific beta keto ester is one that we're going to use a lot in our synthesis. And those of you that are in lab this semester are going to use this in your final reaction in 2 weeks. This is called acetoacetate. Obviously, we would name it by whatever alkyl group is in front. So this might be ethyl acetoacetate. It could be methyl acetoacetate. The most common is ethyl acetoacetate. Do you hear what's in that name? Aceto, which means what?
2 carbons?
2 carbon with a carbonyl. And then also acetate, which means what?
2 carbons and a carbonyl.
So this is acetate that has a substituent aceto group on it. It's a 2 carbon carbonyl with a 2 carbon carbonyl attached. Aceto, 2 carbon carbonyl, acetate, 2 carbon carbonyl. No, that's a terrible name. Bad. I have to use it, so we'll keep using it. But shame on IUPAC for letting that slip. Could we give a systematic name for this beta keto ester? Sorry, that's the more specific name of this. This is a beta keto ester. All we're doing there is clarifying the type of carbonyl. It's not a beta keto ketone, not a beta keto aldehyde. not a beta aldehyde ester. It's a beta ester, beta keto ester. Could we systematically name it? What is the highest priority functional group? The ester. The ketone takes on what name as a substituent? Oxo. Same as the aldehyde. And what position would this oxo group be on? Position 3 relative to the ester. So this is 3-oxo. What's my parent chain? Bute. 3-oxo butanoate. Or we could call it beta-oxo butanoate to, again, clarify that the ketone is on a beta position relative to the ester. What do you think? Are there any other beta acyl carbonyls that you see on your worksheet? No? You do? You don't?
But someone has to guess myself.
Are there any other beta acyl carbonyl compounds on your worksheet? You see one, Christina?
I actually don't know if it is one, but this is like the only other one that looks weird to me that I feel like would have a name.
Well, is there a carbonyl with a carbonyl at a beta position relative to it?
Yeah.
Definitely. Oh, I drew my oxygen. This is called the malonic ester. Like a what? With an A. Yeah. It's nalonic, not melonic. Like there's a difference. Malonic ester. You actually might hear in that word malonic sounds a little bit more like how you'd name an acid. Like benzoic acid, acetic acid, malonic acid. And that's because this ester is named as the ester version of its acid. Malonic acid is this beta carboxylic acid, a beta dicarboxylic acid. Malonic ester is just when you replace the OH groups of the acid with a carbonyl group. I'm sorry, with an alkyl group. And you get the ester. These two beta keto carbonyls, technically not keto carbonyls. Well, this one is a beta ester. You could call it a diester. But if you're relative to one of the esters, it's a beta ester. I know it. And still, generically, you might hear someone refer to it as a beta keto ester. It has some of that similar nature to it. Acetoacetate and malonic ester are two very common precursors in some of the chemistry that we're going to be doing. In section 22, we'll be doing substitution with them. In section 23, we're going to synthesize them. That's fun.
You synthesize from propane?
No, you wouldn't actually want to. You'd want to synthesize them from, one of them from a formate diester, and the other one from like acetic acid, acetyl esters. All right, so we looked at the alpha halocarbonyl, the alpha beta unsaturated carbonyl, and the beta keto carbonyl. This is going to be section 22. This is section 23. These will be used in section 22, but made in section 23. And then there's another one that we're going to make in section 23, and I want to draw your attention to it, and that is I'm actually going to draw this a little bit of a different way. You don't have to get all excited. This is what I call... Actually, I wonder if I can give you guys 5 minutes to think about a way to describe the relationship of the carbonyls here. If it helps, I'll number these positions so that you can kind of make sure that you've drawn your carbon chain correctly. From carbonyl to carbonyl is a 5-carbon distance. Think about, I'll be honest, these other ones, those are names that textbooks use. I invented this name. But it is a product that will be forming in section 23. And if I don't tell you how to recognize the relationship here, then it's hard to find that it exists. But it's consistently this relationship between the carbonyls. And I want you to be aware of it so that you can look for it. But nobody else has given it a name yet. I think I'm the only one, or at the very least, I didn't take this name from anyone else. What would you call that? I didn't synthesize it. So one, that'd be like incredibly rude. Actually, I think this could be named the Michael addition adduct. That would be after the person. This forms from the Michael addition.
Is that your middle name?
No. This forms from the Michael addition, so you could call it the Michael addition product, and that would be naming it after somebody. So we'll give it back to Michael. That's his last name, I think.
That's his last name.
Yeah, most reactions are people's last names, not first names.
It's just a weird last name.
There are Michaels. Come on.
Like
George Michael.
George Michael.
Michael Bolton. In the same sort of way.
Michael Bolton, I think, Michael is the first name there.
I
No?
was saying that's,
Yeah.
oh, what's the last?
Last names. George Michael is a singer, right?
Yeah,
A musician? Oh. Rickroll? The Rickroll guy's name is George Michael? Wow.
So it's written as like
Chad Michael Murray does not count. That is definitely... I thought about Chad Michael Murray, though. Don't we all? What did you say?
No, I was saying it's not. George Michael's not the real guy.
Michelangelo crossed my mind, but
Yeah.
I think that's also a first name.
No, what's his last name? Michaels.
Yeah, Michaels, but that's with an S.
I always thought
What
it
was
was
that?
possessive. Michael's.
Yeah, I think it is an
Like
apostrophe.
his.
Oh. Okay, that might be a first name then. I don't know. All right. Have we debated enough about this? Do you want to shout out ideas of...
Does it have
Oh, shoot.
like trans versus?
It doesn't. I could have drawn this in a different conformation, just in a different wiggliness of it. But when you have a 1-5 position, that means that you're going to have one group up and one group down. 1, 2, 3, 4, 5. Oh, I guess it's not, actually. So you could look at it like this if you wanted to. I guess the reason I drew it in this conformation is because that is how we'll see it most in the Michael addition product. When you connect your carbon chains together, this is what you're going to get. I can give you a hint if you want. What would you call it, Cooper?
Well, I think it's hard because like you can pick whatever group is your priority and then describe it kind of like the like you say like if they're bold esters, you say like quint ester.
We wouldn't use quint, though, would we? I think we'd use something like a pint. Like a pint
Or-
diester.
Or say a pent,
Yeah.
yeah. But I don't know if I like. Well, it doesn't quint though because it's different than what we use for the carbon chains.
Okay, so you kind of want to differentiate it. Say
Yeah.
there's a 5-carbon connection between these 2 carbonyls.
Yeah, because the chain could be, whoever, doesn't matter how long, but you're just describing the connection.
And I'll be honest, the numbers have nothing to do with how I name it. And that was just so you could get the carbon chains right. I actually use some of this other terminology in the way that I name it.
Like shared
Because
data.
What did you say?
I was gonna say, what about like delta keto carbonyl?
Delta. So delta there means what?
It's like the force of like alpha, beta, gamma, delta.
Delta keto carbonyl.
I thought about that too, but I didn't know the Greek alphabet well enough to. I had to look it up.
Me either, yeah. I could have told you gamma, but I didn't know delta came next. I call it. Anybody else have options, ideas?
does it have something to do with the fact that 3 is beta to both of them?
Yes, it does. So, Kayla was right. I call this the shared beta dicarbonyl.
Shared? You say shared beforehand?
Shared beta dicarbonyl. Because that carbon 3 is beta to both carbons. Here's alpha, here's beta. They share a beta position. And this actually forms when the alpha carbon of one carbonyl attacks the beta carbon of an alpha-beta unsaturated carbonyl. Alpha attacks beta. Well, that's still beta to the first carbonyl, but now it's also beta to the new carbonyl. So you get a shared beta dicarbonyl. Shared beta dicarbonyl. I think I think my backup would be the delta. Would we do lowercase or uppercase? You came up with it. Lowercase? Aren't you worried that's gonna make people think partial charges? Beta keto carbonyl. I mean delta.
Well, they should know the Greek alphabet.
Oh wait, that's sigma.
I would just do
No,
the
that was.
delta.
Yeah, little case sigma is this. Okay, sorry, I'm all in a. I don't know my Greek alphabet. Delta positive, delta negative. That's partial positive, partial negative. Okay. Yeah, and we're actually going to use reactions in this unit with heat as the only reagent, and that's delta, so it is pretty hard. All right, so these 4 new functional groups, I want you to keep your eyes out for. Alpha halo, probably the most straightforward. Conjugated carbonyl, okay, makes sense. Beta keto carbonyl, I can see it. The shared beta carbonyl, that one's a little odd, and it's going to be one of the least common of the functional groups. All right? What we're going to get into next is acidity of these alpha carbonyls. And then we're going to look at reactions that form tautomers. I think right now is a good time for a break. So why don't you guys take a minute to get up and move around, get your blood flowing, and then we'll come back in for acidity.
Send an email correcting my mistake. Why?
Why'd you do that?
No, sorry, not correcting. Explaining my mistake. Why? Do people ever email you that they're gonna miss?
Yeah. Isn't that crazy?
I was gonna say that would be nice.
Actually, generally they email me for my Gen Chem 1 lecture, where attendance is mandatory and part of the grade. I don't usually get absence emails for my OChem lectures. Every now and then, when a student regularly shows up and they're going to miss and they just like to keep me informed, they'll reach out. It doesn't usually change much for me. I say, thanks for letting me know. hope you have a quick recovery if they're sick or something.
Oh, you missed
Yeah, what the heck you're doing? Why can't you show up?
priorities.
Am I not more important than your appendectomy?
Are you not entertained? Appendectomy. I've heard some pretty bold claims. I don't think I've ever heard somebody say that they were getting an appendectomy.
Well, I'm in HR, and I have people email me their like sick notes, but my company doesn't do sick time off, which I make aggressively clear to them. I'm like, I can't reimburse you. Like, you
Yeah.
can take the PTO or not. I wish this was my, if I was my policy, I'd change it. But at this point, I've seen like 8 different people's sick notes. I'm like, please stop sending these to me. I don't need to know your medical information.
So what's their the alternative is call in and claim PTO, or how do they claim their PTO?
Yeah, you just call in, claim your PTO on that day, or you just take the loss and have an unpaid day.
Does it have to be on that day that you have to call in for PTO?
No.
So do you tell those people like, this does nothing?
Just tell me later. Yeah. Literally, I'm like, this doesn't do anything for me. Plus, half these people don't even check their pay stubs anyway, so they're just sending me stuff. And when nothing changes 6 months later, I still don't get an email. I mean, it also doesn't help that I found out the people who are running our PTO is a separate company and they have not been paying attention. So I
Dang.
spent my last 2 business days creating full PTO workups for the company. It's been hell. My one requirement when I took this job, I'm like, I refuse to do payroll. I've done payroll. I hate payroll.
Mm.
I miss being in medical because I'm back in freaking admin. It makes more money. And
Yeah.
here we are. And they're like, yeah, sure, you don't have to do payroll. You don't have to do any kind of like payroll, anything. And I'm back to PTO. So at some point, I'm probably gonna walk into their like HR business and I'm gonna be like, who do I need to like shake to get my stuff done?
Yeah,
Like, I
no
need
kidding.
one of you to talk to me. So sorry, you shouldn't have to hear the regalings of HR.
Well, I'm in faculty senate this semester, and faculty senate has a lot of admin in it. They come to share their reports with faculty, and I guess I didn't really think about how many people employed by the college don't teach. They just do paperwork. Like, this is a whole side to the college. The college wouldn't function without HR and without our admin.
HR.
Correct.
Yeah, you need them whether you like it. They don't like to work that much.
And
Everyone just treated each other good. If everyone was friends.
no, HR also does the hiring. They do benefits. They do payroll.
Every once in a while, I used to be an accountant as an HR accountant, personal assistant for a very small company. Well,
Yeah.
a small company, I mean like 30 plus people that made millions of dollars per year. So like, that's that. But
The people made millions, or the company?
the company made millions.
Wow.
They had an owner. So, I mean, that's what happens when you get into like manufacturing and like actual electrical things. So they make
Mm-hmm.
more money than they want to let on. The paperwork side is sucky, but that's what it is.
Yeah.
And I'm in behavioral health, which I never thought I was going to hang out in.
I am kind of glad that I am on the education side and not the admin side.
It's admin is not the worst.
Like, to have to just do paperwork all the time. Oh no.
Well, I think the worst part isn't the paperwork. The worst part is waiting for someone else to do their paperwork so you can do your paperwork. That's the part that sucks.
Mm-hmm.
Everything else is super fun. A lot less action based, a lot more waiting. You got a headache? Well, you still have a headache, but you're double strength, double batch, and then you have like a freezer full of cookie dough, and you're like, just have a pebble, start with a pebble. So I used to be able to get these like sticks,
Yeah.
and you could just dose out with this little bit of caterpillar.
Yeah.
All right. Are we ready to talk about acidity? We don't talk about acidity much, correct?
What?
I just want your perspective. I feel like acidity could be its own class.
Yes.
Yeah.
And
We're really bad at it.
half of organic chemistry is acid-base chemistry, actually.
That's what I just said.
Yeah, that's true, but it doesn't always feel like it. And I want to say that I should do better in my OChem 1 class of putting more of an emphasis on acid-base chemistry because it's so fundamental to all of the reactions we do. The acetal and esterification mechanisms. It's like half acid-base stuff. And while I'm at it, I think maybe I'd like to pick a bone with you guys about some mechanisms. When I give you guys a mechanism, I anticipate that that is the mechanism you will follow. I don't actually want you to show me the mechanism that somebody else might agree with. So here's an example of a mechanism from this online textbook that's free and easy to access. They say, step 1, acyl addition, despite the fact that this reaction should be run in slightly acidic conditions. If it's not run in acidic conditions, then you end up with this intermediate, which is a Zwitter ion, has both a negative charge and a positive charge. And what they claim is a proton transfer. O- and NH2R plus becomes OH and NHR, neutral and neutral. They're not telling you how the proton transfer occurs. They're not even giving you arrow pushing for it. They're just saying, assume proton transfer. And then look at what they show you. Acid. They say, now if you have acid, suddenly your alcohol will become protonated. They don't bother showing it to you. Why? Is it because acid-base chemistry is too fundamental? They expect that you know it already? So they're not going to bother showing you that pesky arrow pushing of that protonation. And then, oh, well, now they've got a deprotonation step, but they don't bother showing you the protonation step. When they say this proton transfer, are they suggesting that the oxygen reaches over and grabs the hydrogen to break the bond back? They're not telling you how they're suggesting the proton is transferred, but many students would interpret it to mean this. Oxygen reaches over. This is not unheard of in organic chemistry reactions to have a transition state that is four-membered. In fact, I didn't get to show you guys this, but the Wittig reaction sometimes has a proposed four-membered transition state intermediate where the carbon attacks carbon and the oxygen attacks oxygen. So that's a four-membered ring. Hydroboration oxidation, where the alkene and borane react simultaneously, that is a four-membered ring transition state. So it's not unheard of. But this is swimming around in a solvent. Typically, a solvent that can transfer protons. So do we suspect the most plausible route is this happening, where it goes into this very high energy four-membered ring to allow for the proton transfer? Or do we suspect that first something runs into this that deprotonates the nitrogen, and then that same thing later runs into the oxygen to protonate it?
Objection. In SN2, the video you showed us of the reaction happening shows like this partial bond breaking and another partial bond forming at the same time,
Yeah.
and like snaps into place.
Yeah.
So is that not evidence of an atom being able to have partial bonds extra than what it should have?
Isn't that what I'm showing here?
Yes.
I'm not, okay. If this is being deprotonated, then this is the transition state. So yes, partial bonds, those dotted lines, are meant to sum up to another total bond. The question is the shape of the intermediate. When they say proton transfer, I suspect that they're saying something in the solvent deprotonates one species and then protonates the next species. And remember that when you're doing a reaction like this, you have like a small number of molecules, just hundreds of millions of molecules, surrounded by a good amount of solvent molecules, typically 100 billion million solvent molecules. Statistically, the odds are solvent is facilitating proton transfer. And we show reaction coordinate diagrams where first it goes over a high energy barrier, and then lower ones, and then lower ones, and then we get to the final product. Killian's brought this up in class a number of times. A lot of times there's nothing stopping a reaction from going forward, and then an intermediate at some time going backwards through a step rather than forwards. Reactions don't happen as seamlessly as we show them in mechanisms. It's not always this molecule packs up its bags, heads to school, heads to work, goes to dinner, and then goes home, right? These molecules are going through a wild number of changes. It's not always a straight line sequence to the final product. It's much more plausible that we suggest something deprotonates this structure and then protonates it again later. That's far more plausible than saying this happens all at once. Other things that I've seen students give me is they'll have proton transfer, but they'll show this getting deprotonated at the same time that this gets protonated. And that feels just as unlikely as this. Okay, you're telling me that the molecule happened to run into an acid and a base at the exact same time? What good fortune. Not just at the same time, but in the correct orientation. The base ran into the part that needed to be deprotonated, and the acid ran into the part that needed to be protonated. That's really good fortune. It is not impossible. It's just implausible. And what's more plausible is that each thing happens sequentially. So I really want to encourage you to avoid mechanisms that just generalize proton transfers, because they are usually saying this is not important enough for us to consider. And I disagree with that. If it exists, it's important enough for us to consider. If it's a plausible pathway for the reaction to proceed, it's important for us to consider. So pay attention to that when you compare the mechanisms that I give you with the mechanisms that you show, especially if you're looking at other resources. See how the ones that I show always emphasize proton transfers as individual steps. Then again, you get into biochemistry and it's a whole different game, right? Because here I'm saying what good fortune that it runs into a base where it needs to and an acid where it needs to at exactly the same time. And that's exactly what enzymes do. They are these massive structures of elements, all bonded in just the right configuration to allow these crazy complex things to happen all at the same time. Which would mean that your acid here is connected to all of this other structure that does come back around and connect to the base, and it always keeps it locked in exactly that configuration. And that also means stereochemistry becomes a lot more relevant. The chirality of these positions is meaningful. One enantiomer will fit in this structure, the other enantiomer or the other diastereomer might not. So we're actually analyzing simpler forms where it doesn't matter the chirality. Biochemistry elevates that to another level. Chirality can make a huge difference. And more complicated things can happen all at the same time, plausibly, because you've got a beast of a machine of a molecule. Whew, okay. So we don't talk about acid-base chemistry that much, but we should, because it is so important. I have this document for you on the homepage of our Canvas course. And the reason that the front page is functional groups and the back page is pKa is because we don't go to it very often. But today I want us to consider this. We don't even need to look at all of those most acidic things. Instead, what we're going to look at is down here kind of in the second half. Let's take an example molecule of 2-butanone. Can you predict the pKa, the relative acidity, of a hydrogen on the CH3 carbon based on this table? I'm going to zoom in a little bit so that the things that are the most relevant are showing up a little bit more clearly.
High, low 50s.
Yeah, high pKa, low acidity. This would have a pKa in the 50s to 60s. You're saying low end because it's less substituted. And we've actually talked before a little bit, we should have talked more about it, about how more substituted groups tend to be more basic because of greater electron repulsion, trying to get rid of that excess negative charge. This would be on the slightly more acidic side because it's less substituted. But still, essentially not an acid. There is almost nothing that you can react it with that will take away that hydrogen from the carbon. So how do you deprotonate this type of carbon? You don't. Plain and simple. If you wanted to have the conjugate base, then you need to have that carbon be an alkyl halide, and then react the alkyl halide with a metal like lithium or magnesium. Now you have the carbanion bonded to lithium or bonded to magnesium, the organometallic. That's the conjugate base. And how acidic is that? I'm sorry, how basic is the organometallic? Very basic. It deprotonates anything. What about this position here at the alpha carbon? And to be fair, we can say either position at the alpha carbon. 15 to 25. Why? But I mean,
But also, it kind of makes sense because it's nearer to an oxygen, so there's like more pull, like negative pull from that oxygen makes the hydrogen easier to steal because the oxygen's pulling the electrons towards it.
so you're blaming induction. Here's a way that we could look at this. To blame it on induction, what do you think the acidity of the hydrogens in dimethyl ether is? Would you say that these are equally acidic, as the alpha position less acidic, more acidic than the alpha position?
Oh, more.
More acidic. So they'd have a pKa less than 20, maybe towards 10.
Well, why not?
Talk about what else has a pKa near this range. In the realm of alpha carbon acidity, what else is in here? Alkynes are not in this. Okay, alkynes are on the upper range, true. Alcohols are on the lower range. So some carbonyls have alpha positions about as acidic as alcohols. Some have alpha positions that are about as acidic as alkynes. That's like a good range of acidity. That is a 10 to the 10 order of magnitude difference. So some alkynes are 10 billion times more acidic than other. I didn't mean alkynes. Some alpha carbons are 10 billion times more acidic than others. If it were based on induction, then we should say that this is more acidic, but it's not. The pKa here is still in the 50s to 60s. That's because this is an sp3 hybridized carbon. And so similar to the other sp3 hybridized carbons, very, very basic, not acidic. Let's not credit it to induction. There's another feature of the conjugate base that stabilizes the conjugate base and drops its pKa, making it more acidic, less basic of a conjugate base.
Is it the higher substitution?
Not substitution.
Not the alkoxide?
Resonance. It can store that new negative charge not on the carbon, but on the oxygen. This is called an enolate.
So a pi bond on the carbon is what would break first?
Pi bond on the carbon? I don't see a pi bond on
You
the
have
carbon.
an sp2. Oh, there already isn't. There already is a free p orbital.
Okay. Resonance increases its pKa. The fact that it has resonance in the conjugate base increases its pKa. Let's make some comparison to some other carbon hydrogen groups or some other resonance things that we know have resonance in the conjugate base. Let's look at phenol. When the OH gets deprotonated and gives us O minus, there is resonance into the aromatic ring. I'm just showing one of those resonance forms. Do you remember the relative pKa range of the phenol? Not 6? A little bit higher. 10,000 times higher. 10. From 6 to 10 is 4 orders of magnitude, which is 10,000. Why is phenol 10,000 times more acidic than, or 100,000 times more acidic than our most acidic alpha carbon? More resonance. Despite the fact that those additional resonance forms are actually all on carbon as well, it is increased resonance that makes it more acidic. So, an alpha carbon with more resonance will always be more acidic. Let's look at the factors impacting acidity. There's a few main factors to consider. First is the functional group. The functional group can impact how acidic we see things. I'm going to be drawing in the acidic hydrogens here with this red H. Also, this gets a lot of students, this trips a lot of students up. They will look at this and suspect that the aldehyde hydrogen is more acidic, but the aldehyde hydrogen has no resonance in the conjugate base. The alpha hydrogen does have resonance. Aldehydes versus ketones versus esters. How do you think acidity ranks between these groups? And I will tell you they're in order. You just need to decide, is it increasing order or decreasing order?
PK.
How does their pKa rank here? What would you suspect?
It's decreasing, so it gets more acidic the right it goes.
Decreasing pKa, more acidic to the right. Any other thoughts? What do you suppose? How would the nature of these other groups change the acidity? As I swap a hydrogen for a carbon chain for an alkoxy chain, I have some numbers, I'm pulling them up. But I want to hear a debate. Oh, well, sorry. Actually, there is resonance in the conjugate base for each of these.
Oh yeah, but there's just less. I would think less forms possible.
Same number of forms, actually. Let's look at the conjugate base that forms. Here, the conjugate base
Well, the alcohol.
is here, 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 and the resonance form. Oops. Now I have an alkene and O minus. Alkene and O minus. Alkene and O minus. By the way, that's why it's called enolate, is because it's an alkene with this alkoxy group on it. It's actually, we're going to learn, it's the conjugate base of an enol. Say that one more time for me.
Can the negative charge land on the other oxygen?
It can't.
No.
This oxygen has an octet already. So this oxygen could actually share electrons to the carbonyl, but it can't take electrons from this system. So there is another form. Oh, sorry, I forgot my O here. There is another resonance form for the ester. It's a bit of an odd one. What does that tell you? It's not a favorable resonance form. It's got maximum charges. But actually, none of the other groups, the aldehyde and the ketone, can't make that resonance form. Correct? They can't make this because the ketone has no group to share. The hydrogen can't share. Do you think this resonance form stabilizes the conjugate base or destabilizes the conjugate base? Destabilizes, making this the least acidic alpha hydrogen.
You also, like we discussed before, like aldehydes are the most reactive, but you just kind of assume aldehydes are more reactive than ketones without.
Well, they're the most reactive carbonyl carbon, so they're the most reactive electrophile. And this is technically electrophile as well, but it's not so much about the partial positive of the. Yeah. And this is terrible. It's actually not letting me in to find my numbers. Oh, here we go. So the increasing order here is to the right. I'm sorry. Increasing pKa to the right, decreasing acidity. And it, oh, you know what, Maddie? I guess it does have something to do with the H. This is induction. So the aldehyde is more acidic than the ketone, is more acidic than the ester, least acidic, most acidic. And we can actually blame it on that resonance form on the right-hand side. We might also be able to blame it on just general induction. The hydrogen doesn't have a lot of electron density, which means when the negative charge forms on this enolate, whether it be on the carbon or the oxygen, the hydrogen is not disturbing the negative charge very much. But this carbon group of the ketone, it has a lot more electron density, which disturbs this negative charge and makes it act as a base more. And the oxygen has not only more electron density, but it can share its electron density, destabilizing that negative charge. So you might organize this as aldehyde, ketone, ester in order of decreasing acidity, or you might say it's because of induction. I'm still looking for them. Unfortunately, I didn't bring my iPad, and that's normally where I keep them. And this is being very rude to me. It's not letting me sign in. I don't want to throw out numbers. I could guess at my numbers, but I don't really want to, so we might come back to those pKa's. All right, now let's hone in on one of these functional groups. Let's take an aldehyde, and let's look at how the degree of carbon substitution changes and the pKa changes with that. If I have a primary alpha hydrogen, a secondary alpha hydrogen, a tertiary alpha hydrogen. I'm not going to show a quaternary alpha hydrogen because it doesn't exist. Yeah, it really hates me, unfortunately. What do you suspect? And for each of these, let's draw the conjugate base in both of its resonance forms. I'm going to do that again in two different colors. Go ahead.
most substituted would have the lowest pKa.
The most acidic at the most substituted?
Yes.
You want to argue why?
Well, substitution is more stable. Don't remember why that is, but it is more stable.
Mm.
More substituted
More substituted is more stable.
for negative charges.
No. Actually, quite the opposite.
Oh.
Positive charges are more stable on more substituted carbons.
So then backwards, the least substituted
Okay.
would be the most acidic.
Do you guys hear what Killian is saying, and do you agree? The negative charge is disturbed by more carbon substitution, by more electron groups. So the more electron groups around it, the more basic it would be, the less acidic it would be. Do you agree? Sound off.
What?
What's the most acidic? What's the least acidic? Do you agree with Killian's designation? How does the nature of the other resonance form change your opinion? Does it? Which of these resonance forms is more stable? Which of these is a more major contributor? Why? Exactly. More electronegative, holds on to the negative better. There's octets between both resonance forms, so it's not about number of charge, it's not about number of octets, it's all about placement of the charge. So we should be analyzing the stability of this resonance form in the same way here. The hydrogen doesn't push much on the O-, so it's not very basic. The carbon pushes more on the O-, and now we're seeing the oxygen pushes a lot on the O- and the carbon minus. What's the difference between these red resonance forms? The substitution of the alkene. We describe this as unsubstituted. This is mono-substituted. And this is di-substituted. Do we remember anything about the stability and the reactivity of alkenes? More substituted alkene, more stable. So, Killian, I loved your train of thought. More negative charge on a negative charge on a more substituted carbon should be more basic. But when we look at the more stable resonance form, the major contributor, that is the most stable alkene. So carbon substitution by stability of enolate.
Because
This is less acidic. This is your least acidic. This is your most acidic. And I did get numbers, so we can come back and look at the numbers. What did you want to add?
because the oxygen can deal with the negative charge just fine.
The oxygen deals with the negative the most. Yep. And because of that, we look at the shape of the alkene. I'm saying stability of enolate, and what I really mean is the ene of the enolate, stability of the alkene in the enolate. For numbers, the aldehyde typically has a range near 17. So here we can say the pKa is about 17. The ketone has a pKa around 20. And the ester has a pKa around 25. So that's a pretty drastic change in pKa. Remember that pKa is logarithmic. So each number is a factor of 10. That means that aldehydes are 1,000 times more acidic at the alpha position than ketones. And ketones are 10,000 times more acidic at the alpha position than esters. That is to say, for every one ester alpha hydrogen that's deprotonated, there would be 10,000 ketone alpha hydrogens that have been deprotonated. Think about that in terms of statistics. If you have both an ester and a ketone, which one gets deprotonated? The ketone. Here, orders of magnitude stay a lot more close together. This is, again, about 17 in terms of pKa. This is about, oh, actually, I'm sorry, I think I have my numbers backwards. Oh, yeah. 17, slightly more acidic, about 16, slightly more acidic, about 15. So that's 10 times more acidic, 100 times more acidic, but not as drastic as 1,000 times more acidic, or 10,000 times. Or from 17 to 25 is 10 to the 8 orders of magnitude, which is 100 million times more acidic between aldehyde and ester. All right, the last thing that we have to consider here is how acidity changes with amount of resonance. And so we bring back our two main hitters, malonic ester and acetoacetate. We know that the alpha position of an ester is about a pKa of 25. But for this conjugate base, I may have drawn these too close together because I actually have a lot of resonance forms to draw.
Four resonance forms
No, 3
for each?
for each. If we look at the alpha hydrogen, this is an alpha hydrogen to both carbonyls. When that gets deprotonated, where can my negative charge go? It doesn't just go to one of the two esters, it can go to both of them independently. Three resonance forms. Remember that we argued phenol is more acidic than the carbonyl carbon because there are more resonance forms. And here we're saying that this alpha carbon still has resonance forms. That increases its acidity relative to a typical sp3 carbon. So now if I can double, oh, that's not double, is it? If I can increase the number of resonance forms by 50%, not to mention these resonance forms, 2 of the 3 of them put a negative charge on O. Only one of them puts a negative charge on the carbon. What do you think the pKa of this position is? Higher than 25, equal to 25, or lower than 25? Sorry? Lower. I'm increasing resonance. It should be a more stable base, a more acidic alpha hydrogen. higher than 17, equal to 17, or lower than 17? Higher? So you feel like the substitution of the aldehyde's alpha carbon could have a 100 times impact on its acidity, but you think that increasing the number of resonance forms to have twice as many resonance forms where O is holding the negative charge doesn't even have 10 to the 8th times the impact? Actually, let's make one more comparison. From a typical sp3 to an sp3 that has resonance with an oxygen, that is an order of magnitude change of 10 to the 30. Being in resonance with a carbonyl makes the sp3 carbon 10 to the 30 times more acidic. That is an unfathomable distance. Now, double the amount of resonance that includes a negative charge on oxygen. And you're saying that it's not even 10 to the 8th times as much of a difference? The last time we added oxygen, it was 10 to the 30. Double the amount of resonance forms where oxygen holds the negative charge, the pKa drops to 13. That is 10 to the 12. So still not as drastic as 10 to the 30, but very impressive.
What's the pK of acetic acid?
About 5. So it's still not as acidic as an acid. It's not as acidic even as phenol. But it is more acidic than a number of other things. All right, and our last one was the acetoacetate. First, let's recognize that this pKa of this alpha hydrogen is about what? Alpha hydrogen of a ketone? About 20. Give or take a few orders of magnitude, depending on its degree of substitution. But now the pKa of this center alpha hydrogen, do you suspect that this is more acidic, equally acidic, or less acidic than the malonic ester? And I'm going to draw out its 3 resonance forms for us. Same number of resonance forms, same degree of substitution, same number of resonance forms where oxygen holds the negative charge. What's the only difference?
The extra oxygen.
The extra oxygen, can you describe that a bit differently? The difference between malonic ether, I added an extra carbon chain on that, but it doesn't really matter. The difference between malonic ester and acetoacetate ester? Ester versus ketone. One is a diester, one is a ketoester, beta ketoester. How do we compare the acidity between ketones and esters? If that's the only difference, is that you substitute a ketone and an ester, how do you compare the acidity between ketones and esters? Esters are less acidic. So the acetoacetate, more acidic than malonic or less acidic than malonic ester? Or does it not make enough of a difference that it should just be relatively the same? What does your gut say?
I want to say no.
They're equal?
Yeah. I would say they're equal.
So here the difference between a ketone and ester didn't matter, but here the difference between a ketone and ester was the difference of 10 to the 5 orders of magnitude. More acidic because I swapped out an ester for a ketone. That's what functional group trends would say. How much? Do you think it's more acidic by the same difference, 10 to the 5, or a little bit closer? What you're developing right now, the questions that are turning, is chemical intuition. Chemical intuition is built by exposure to examples. You have to think about what you might expect and then see the reality of it, and you build your chemical intuition, your expectation of what can and should happen. Functional group changes from something that is less acidic to more acidic, and the pKa changes. pKa of 11, not quite as big of a difference as the last time we saw ketone versus ester, but still 100 times more acidic just by being a ketone. I have taken us pretty much right up to time. What I wanted you guys to do was look at these different examples and predict how their acidity will change. One thing I want you to recognize, the acidity over here on these non-alpha carbons, that's always very high. The acidity of this is in the 50s to 60s. The acidity of the aldehyde hydrogen, that's incredibly high. In fact, I want to say it's more than 50s to 60s. This is very not acidic. So I want you to look at these. If there are any that stump you and you're like, well, I don't know how to compare this one versus that one, then think about that. This is where we'll start off on Wednesday, and then we're actually going to take advantage of this alpha carbon reactivity, and we're going to draw tautomers. I think those of you that were in my OCHEM 1 class, I taught you this word, tautomer. Do you remember what it means?
Change in pi bonds? They keep the bonds?
Good. All of those were correct. Keep the number of pi bonds, but rearrange them. That's describing structural isomerism, specifically between ketones and enols. Not just alcohols, but alcohols connected to alkenes. We're going to see that we can do this only for positions that have alpha hydrogens. The alpha hydrogen is being structurally isomerated into a new position, and that can be catalyzed by base, and it can be catalyzed by acids. And we're going to use those tautomers, those structural isomers, specifically by rearrangement of a pi bond, to take advantage of our substitution reactions. So that's where we're headed on Wednesday, and we're going to look at reactions on the back. So if you want to get started, rank your pKa's and start looking at tautomerization. That's where we'll pick up Wednesday. Yeah, here they shared the same number of resonance forms. They also share the same number of resonance forms, but there's a harder emphasis on the number with oxygens, so the difference kind of narrows in. Good question. Have a good night, everybody.